So, hello everyone. In this video we will be demonstrating how to create a taste application that uses an FPGA component. So parts of the functionality of the system will be implemented basically in hardware. And we will do this from scratch. So this is the default screen that you see when you boot the Taste virtual machine, which by the way you can download from here using the taste.tools URL. Taste.tools. You go to the download area and then you select the Taste virtual machine file, which you then import into VirtualBox. And when you boot it inside VirtualBox, the first screen you see will be this one. So let's create a VHDL demo folder and start creating a taste project in here. So taste will start by creating a skeleton for with the simple types used for the data view and an empty interface view and an empty deployment view. Let's start with a data view that describes the types exchanged between the subsystems of our design. The sample generated by taste contains just a type, declaring that it's identical basically to a Boolean type, sorry. But we will do something a little bit more complex. We will create a type myInteger, and in fact we will make it an integer that isn't this small. We will create something with a little bigger range, so let's use really big integer ranges. So we'll paste it here. And we will also use a type that has a sequence, which is ASN1 terminology for a record or a struct, basically an accumulation of fields. And this struct will have an X of type myInteger, a Y of type myInteger, and a Z type myInteger. Now I'm not using reals deliberately. As you can see, reals are available in ASN1, but I'm not using them, and the reason I'm not using them is because reals correspond to floating point values, floating point computations in taste designs, and in FPGAs floating point computations is not a good idea. So we'll keep it simple here. We'll have just an input type used in our interface towards the hardware, which has 3 integers in a sequence, and the hardware will output an integer value out. So let's do just that. Let's describe this interface in our interface view. So I will create a new function which will be written in C, and it will speak to hardware. And I will create another functional block. Note that the term function here is not what is usually used for in normal programming languages. Function in terms of taste is a set of functionality. It's a functional block really that contains interfaces implemented in the same language. So this second functional block contains VHDL code, and it will be named appropriately, so something like FPGA logic. So inside the FPGA logic, as we described before, we will have a provided interface. So basically the FPGA logic functional block will provide, hence the P, provided interface, will provide a compute something interface, which will also be a protected one, meaning that it will be it will serialize the callers through a semaphore or a mutual exclusion functionality anyway, that will protect from race conditions. If multiple threads, multiple tasks were calling compute something at the same time, we wouldn't want them to mess each other's results while talking to the hardware. And as we said before, it will have an input parameter, imp, which is of the type sequence that we described before, with the three fields x, y, and z, and it's an input parameter, and it will have an output parameter called outp, which will be an integer. So that's it. We created our first interface that our hardware will provide. Then our C side obviously needs to have some interfaces of its own. First of all, it will have a cyclic interface. Let's call it pulse, which will be executing every 1000 milliseconds. Now, this interface, this pulse, will be called by the environment, and the environment is, it depends on where we deploy. So we will see later that when we deploy our functional blocks into target nodes, we can specify that something is, for example, a Linux node, or a Leon 2 Artems node, or a Leon 3 node running the Artems operating system, or a GR740 board running the Artems 4.12 operating system. So depending on what is your target deployment, there are specific APIs that Taste will use to call this pulse every 1000 milliseconds. pthread create will be called under Linux to create a thread that calls this, or Artems task create will be called for Artems, and so on and so forth. Regardless, when this pulse is called, it needs to invoke the hardware, so it requires another interface to function. So it has a new required interface which we connect with the provided interface from the FPGA. And that's it. Our interface design is complete. We save it and we ask Taste to create the skeletons for our design. And while Taste is doing this, let's have a look. So I'm exiting from Python, and you see that this folder, which was initially empty, now has ADL files that describe the interface view that we have created, and the ASN1 files that describe the types that we are using. And because of the specification of the interface view, Taste is in a position now to create the skeletons for the two functional blocks. So the speak to hardware C part, which is on the left, has some C files generated that contain the skeleton for the implementation, and the FPGA logic ones also have a set of files, in this particular case Xilinx ISC files, project files, as well as VHDL files, which we will see soon, where we will go in and fill the functionality that we need. And indeed, let's do so. So we go to the C side first, and we edit the C source code. So we see that there is a startup function which Taste will call upon initialization. So for every functional block there's a sort of entry point, and we just use C's APIs to specify what we want to print, and we will print when this is called. And then Taste will start calling our pulse every 1000 milliseconds. So what do we want to do here? Well, we want to call out into the hardware. We specifically said in our interface view that we have a required interface, so a requirement to call someone else. And Taste translated this into an external declaration prototype, which we just copy here. And the important thing to understand here is that we don't need to specify how exactly this call is made, because based on our design, based on our interface view and our deployment view, which we will soon create, Taste will know what kind of primitives it needs to invoke to transfer the call across to whatever other entity is supposed to service it. So in this case, where we have an FPGA, this call will be forwarded over to a device driver that will speak with the FPGA. But we don't care about this. All of this is abstracted and basically generated for us automatically based on the models of our design. So we see that the array has basically two parameters, a pointer to the input variable and a pointer to the output one. Let's declare those variables. So we'll declare them here. So we have an input variable and we have an output variable. Let's initialize it, and in fact let's make it a static as well so that it survives across multiple calls of pulse, because I want it to be able to change the value of this input structure. I initialized it so that x is 0, y is 1 and z is 0 the first time, but then every time this is called I want to increase these so that we will be able to see some difference in what happens in terms of what the output, the hardware part returns. So I pass a pointer, as the prototype suggests, to the input variable, and I also pass a pointer to the output variable. And that's it. My specification of my implementation of the C side of this design is completed. The only problem is I haven't printed the results. I won't be able to know what exactly happened. So let's add this. So the speak to hardware PI pulse sent this value, and this value to the FPGA and got this value back. So what did we send? We sent input.x, input.y, and input.z, and we got back output. So we're done with implementation of C. Let's now move to the implementation of the VHDL side. So in the same manner, I added VHDL. And note that in this virtual machine I have also installed the Xilinx ISE using for demonstration purposes the Webpack license. Now this isn't packaged in the VM because of obvious licensing reasons, but you can install it from the Xilinx website. And as you can see, ISE opened the sample design that was created, and if you remember, we had a compute something interface described in our interface view, and indeed we have this, the corresponding skeleton, in VHDL. So we have, from the input parameter, the field X, the field Y, and the field Z have been transformed into STD logic vectors. Now the output parameter has also been translated into another output vector. Since this is circuits we're talking about, obviously we have a clock and a reset for digital circuits, and there's two additional signals. There's a start compute something and a finish compute something. So basically the taste skeletons, in addition to what you see here, for the FPGA there will also be a driver generated completely automatically based on your design, based on your specification, on the model that you're using. And what this driver will do, we will see it actually soon in the code that will be generated. It will map all the input parameter values into these input signals, and as soon as it does this and writes to the appropriate registers to populate this information inside the FPGA, it will then raise this flag, it will raise this bit, and the FPGA state machine waits for this. So we'll see below that in the skeleton that was generated, we have a very simple state machine that begins at wait for start signal, and as soon as the flag is raised from the device driver that Taste will generate, telling us that okay, all your inputs are there, start processing, we move to the signal received and we do our work. Now, I'm a software guy, not a hardware guy, but I think I can write this properly, which is to do something with the inputs. So let's, what was it, input underscore x. So let's add the 3 inputs that we got from the input parameter and assign it to the output. As soon as we do this, the skeleton, as you see, moves the state machine to work done, where it will raise the finish flag, the finish compute something flag. And the device driver is basically waiting for this. As you can see here, this is an output STDA logic. It waits for this to be signaled, and then it will take the output parameters, populate the appropriate values, and return a response to the caller. So that's it. We just implemented the logic for the VHDL side. So let's save everything. Let's do some. Let's invoke the synthesis of the Xilinx ISE, which processes the top level, of course the VHDL code we wrote, and hopefully reports that it completed successfully. So we move to the next step, implement design, with the intent in the end to generate, of course, a bit file that we will burn in our FPGA. Placement and routing. Also done. And generation of the bit file. So we will see generate the program completely successfully. We will see here that there was a bit file generated. Just to prove it, that was just built now. There was a bit file generated from our FPGA design. So that's it. We have managed to successfully compile our VHDL skeleton. We go back into the IDE, and now there's only one step remaining, which is where we will be deploying these blocks. So in our deployment view, in this case, this FPGA only works under Linux board, so I'll just take the x86 Linux node and copy it in the deployment view, and I will allocate basically both these functional blocks in the same target node in this x86 partition. So in this case, the deployment of the FPGA block obviously does not refer to the hardware parts, because those run inside the FPGA. It refers to the driver that is automatically generated to communicate, to speak with the FPGA at runtime. So the software driver will be running in the same partition as our test speak to hardware logic runs. So I save this, and moment of truth. I build the system. Notice that the build can also be done from here. We have a build script that you can call from the outside, and the same also applies to the FPGA. There's a make file where you could do make in there to build your bit file to see it the way it's supposed to be done. So from within the UI, we see that the build completed, and it reports that there's a VHDL bit file built here, and also a taste binary named appropriately x86 partition, because this is what we named it in the deployment view, which we can run. So I might as well now plug the FPGA in. And let me also start taking a video of the process with my camera. So let me see. Record. So this is the FPGA. I hope I'll be able to place this video in the recording later. Attached over USB to my laptop. And I have to also specify here, because this is a USB attached FPGA, that I want it to be controlled basically by the virtual machine. So I just moved it in there, and now I'm just going in the folder where the binary was created. So binaries, and I will execute it with root permission. And lo and behold, everything seems to be working fine. I sent 0, 1, and 2 to the FPGA, and I get 3 back. 1, 2, and 3 after the plus plus from the C side, and I get 6 back, and so on and so forth. So that's it. This is how, this is the principle of how Taste handles FPGA devices. Basically, very similar patterns to what we do with the rest of the modeling languages that we support in Taste. Now, before I complete this presentation, let me also show you what kind of work the device driver that was generated is doing. So you'll see that in the glue that was generated for the FPGA logic, there is a for the compute something interface. There is a file that provides the basics of speaking to the FPGA in terms of converting the inputs to write them to the appropriate registers, then raising the flag to tell the FPGA to start processing, and wait for it to say, okay, I'm done, and then reading the outputs from the FPGA registers and creating a response back. And you see that all the necessary details, for example, the waiting for the flag to be set, and the processing, the mapping of the inputs and the outputs through the appropriate FPGA specific, of course, register APIs, are all generated by Taste for the specific FPGA target. Another thing to notice is that you don't need to care about something that hardware designers and device driver writers care a lot, which is this kind of offsets, because by knowing your interfaces and their specifications, the Taste code generators can allocate the fields of the input parameters to the appropriate offsets that are big enough to hold them. So in this case, because the 3 input parameters were 8 bytes wide, you see that the first one is at offset 1, the second one is at offset 9, and the third one is at offset 17. And if you're wondering what is at offset 0, it's the 2 magic bits, so the start working and tell me when you're done. But the point is that if you decide to go back to your specification, and instead of having just X, Y, and Z, you decide to introduce another field in between X and Y, or something even more complex, a field that is a sequence or whatever, you don't have to think about how you maintain these offsets, because the driver again will be written automatically for you, and the skeleton as well, and so on and so forth. So as long as you do it right, okay, in this example I just blasted the code directly in the skeleton on the VHDL side, but if you had a component, if you have your code in a component form, you basically just connect the wires and you're done. And you will be able to do this as you evolve your design and your implementation. So that's it. I hope this video clarifies how Taste works with FPGAs. Thanks for watching.